Okay. I had to. This homework was originally due tonight, but I shifted it back to Wednesday because we had to take the material a little bit out of order. So we really haven't talked about this material yet. So some of you have worked on it blindly, okay? But we'll talk about that. All right. I was trying to get to it last time, but I never got quite to that part. Okay. But we'll get to that immediately today. And then we have this quiz coming up also, which is over these two sections, right? Okay. So this one you've already turned in already, right? Slight there adjustment to the homework schedule, and I think we'll have time next time to after the period to work on finishing those two homeworks. That homework and that quiz, okay, which currently are due there simultaneously, right? So that's kind of where we are with the assignment. I don't think either one of those people are here. Yeah. Tajane wants it there, but neither one of them are there. Yeah, Nicolette's back, right? So who's that? Salma. Salma's usually sitting right there, right? But I don't see her. Okay. All right. Do you have any questions off of any of the homeworks? Currently. All right. So you want to be sure to bring your homework questions, right? Okay. So that I can answer them in class, so that everyone can hear the answer. So be thinking about what things are causing you issues on the homework. All right. So we can discuss those when we have the opportunity in class. All right. Let's just remind ourselves of what we were doing last time. And so we were trying. The last thing we did in lecture is try to write down the formula for a line where we're either given the graph of a line, or in this case, not quite the graph of a line, but we're given 2 points off of the line, which is essentially the same as having the graph, right? Okay. Because it's easy to graph the line that passes through those 2 points, right? So you can almost visualize what that line is going to look like, right, in your mind. This point is in the second quadrant. X is negative and Y is positive, so it's to the left of the y-axis. I'm sorry, to the left of the y-axis, but above the x-axis. And this point is in the first quadrant. Because both x and y are positive, so you've got a line there connecting a point in the second quadrant to a point in the first quadrant, right? So again, it's kind of easy to visualize that, even if you don't explicitly have the graph drawn for you. But it's not the graph that we're after here. What we want to do is write down the formula for that line, right? Okay. So that's our goal. And that was the last thing we did in the lecture last time. We had one example of that. So here's a second example of that. And then I'm going to show you, we've seen other examples too, but and then I'm going to show you kind of a little shortcut to this process, okay? That kind of makes it easier or almost automatic to solve this kind of problem, if you can remember that. If you can remember that shortcut, right? Okay. So, all right. So there's the problem that presents itself, right? And we have to remember, here's really crucial in almost every situation now where we're given some points on a graph, and we're told something about a curve that passes through those points. Okay. And we want to write down the formula for that curve. It doesn't have to always be a straight line, okay? Because we're going to learn about other curves other than straight lines. But in any of that, those types of problems, you really do have to know, have some sort of description of what the curve is supposed to look like, right? Because you can have lots of curves that pass through different points, right? You can have curves of all types of shapes that pass through points. So if you're just asked to write down a curve that passes through some given set of points, that's really not enough information to solve the problem, right? Because there's lots of different possibilities, okay? But here we know it's a line that passes through these 2 points, and once we know it's a line, then that really sort of gives away the problem, because we know what the formula is going to look like, right? Okay, so that's the real key thing that you want to start with with this problem, is to remind yourself, oh, when I'm finished, right, I'm going to have a formula that looks something like this, okay, because that's what linear formulas look like, right? Okay, and so our goal here, our task here, is only to figure out what goes in for the m, right, and what goes in for the b, but we know how to discover those things, correct? Okay, we know what the m is, right? That's the slope of the line, right, the rate of change of the line, and we also know geometrically what the b is. That's the y-intercept. So if one of these points given to us is the y-intercept, then it's easy to fill in the value for b. Unfortunately, though, neither one of those points is the y-intercept, correct? Okay, because with the y-intercept, the x-coordinate is going to have to be 0 for the y-intercept, right? Because y-intercept is on the y-axis, and every point on the y-axis has x-coordinate 0. So neither of these points is the y-intercept. All right, well, that's okay, though, all right? We'll figure out what the value for b is, right, without explicitly it being given to us. So let's start with this value m, of course, and we know that to be what? I just said it, right? What is m? Slope, right? That's the slope, right? Okay. So and we have a formula for the slope, right? Okay. So we can figure out here what the slope is. So we have lots of ways of figuring out what the slope is, right? By reminding us actually what the slope stands for, right? Remember, that's the change in y, right? When x increases by 1 unit. We don't have that information given to us, okay? We don't have that information given to us, what the change in y is when x increases by 1 unit. But that's okay, because we have these 2 points. And we also can calculate the slope, right, from 2 points, because we have a formula, right, from 2 points for calculating the slope. That's right. So that slope formula is y2 minus y1, right, okay, over x2 minus x1. Remember, this quantity in the numerator, y2 minus y1, that's often called the rise, and this quantity in the denominator, come on, guys, really? That quantity in the denominator is known as the run, all right, okay? Just as a shorthand device to help remember those values. All right, so, well, let's just fill in our coordinates, right, for x and y, okay? So remember that formula y2 minus y1, right? That just means take the difference in the y coordinates for the 2 points you're given, and you can do that in either order, right? Okay, so if you want to here, you can do 2 minus 6, or you could also do 6 minus 2. Either way will work. The only thing you have to remember is in the denominator, where you take x2 minus x1, make sure you do the subtraction in the same order. Otherwise, you're going to end up with the sign incorrect, okay? Sometimes you can double check that if you get the sign wrong, because you know, right, that lines going uphill from left to right, they have to have positive slope, and lines going downhill from left to right, they have to have negative slope. So if the sign of the slope that you're given doesn't correspond to the picture of the line, then you know, right, that you can just change the sign, right, okay, or you can look for your mistake, all right? Nicolette, you don't have your phone out, do you?
No, it's my phone.
No, okay, all right. So, so when we're taking this difference in the bottom, right, okay, let's do this as same way that we did it in the top. Let's take 2 minus a minus 3, okay, right? Be sure you pay careful attention. Be sure you pay careful attention to the signs, and don't let yourself make a sign mistake. This is 2 minus a minus 3. So ultimately, that's going to end up as plus 3. Okay. So that is a frequent source of mistakes for everyone, me included, right? Are letting yourself lose track of signs like this, right? This minus sign is part of the formula. This minus sign just comes from the fact that this x-coordinate is minus 3, right? Okay. Oh, by the way, one thing I want to caution you about. This showed up in the tests, not just in this class, but in other classes too, where I was giving tests last week. Look, you cannot put two arithmetic operators, you cannot put them side by side in mathematics without having them separated somehow. So the parentheses here are really necessary. You couldn't write 2 minus a minus 3 without the parentheses. That is incorrect syntax, okay? So if you've got any sort of math operator, it could be addition, subtraction, or it could be multiplication, right, where you have a dot, for instance, right, okay, or division, where you have a division sign. Don't put the two operators side by side without separating them somehow, okay, typically with parentheses, okay, like I've written it here. That is a source of all kinds of, it's bad mathematics syntax for a reason, because it's going to lead to all sorts of mistakes, okay, when you do that. So just whenever you are tempted to write two math operators side by side, you're going to have to think about that. No, I cannot put two of them side by side without separating them somehow, okay? Just not going to work. All right, so let's see, what do we have here? Minus 4 over what? Positive 5? Okay, so we get a negative slope there, and I think that's correct, because if you think about, if you visualize those 2 points, okay, I think you can see this point's a little bit higher than this one. So this line is going downhill from left to right, right? Okay, so we should have a negative slope, right? That does correspond to the geometry of the situation. Now look, that means you're halfway through. That means you're halfway through with the problem, okay? Because now you know what the slope is, all right? So you can just fill that in, okay? Because now you know that the slope is minus 4/5. So let's write that down. So we know the line is y is equal to minus 4/5 x plus b, okay? Minus 4/5 x plus b. And then, how do we find the b now? Yeah, Arthur. That's right, okay? We know that this formula that we write, okay, that has to correspond to this line. That's the whole point of the problem, right, is to write a formula that matches this line. That means then that these coordinates have to satisfy this equation. So, for instance, if you plug minus 3 in for x and 6 in for y, the equation would have to be true, okay? Or the same way, if you plug 2 in for x and 2 in for y, you know the equation has to be true. So you can do that then, plug in the values for x and y, and that leaves you an equation with just the variable b, and it's easy to solve that equation for b. So you can figure out sort of backwards, right, what the y-intercept is supposed to be here, okay? All right, let's try plugging in the 2 and the 2 for no good reason. Maybe this was the easier point to plug in, but so I'm going to plug the 2 in there, right, okay, and for y, and also the 2 for x. And then we're just left with this little equation to solve for b. That's pretty easy to solve. Let's see, I have 2 is equal to minus 4/5 times 2 is minus 8/5, right, plus b. And now you can isolate the b, right, just by adding 8/5 to both sides. So I have 2 plus 8/5 is equal to b. And now I have to add 2 and 8/5 together, okay? If you just have to, you can do this with your calculator, all right? But this is not so bad, not so challenging, right, that we couldn't do it pretty easily just by hand. And that's just converting the number 2 into fifths, right, okay, so that we can add these two fractions together. So we just have to ask ourselves, how many fifths is the number 2? So how do you write the 2 as a fraction with fifths as the denominator? How many fifths is the number 2? What? Yeah, it's 10 over 5, right? It's 10 of them, right? Because 5 divides into 10 twice, right? So that you can just deduce, right, by inspection that 2 must be 10/5. So we end up here with our y-intercept as being 18/5. And we can just leave it in that form, all right? There's no really reason that we have to convert that to decimals. And in fact, we may not want to convert it to decimals. So I have y is equal to minus 4/5 x, right? The slope times x plus the y-intercept there, which is 18/5. Okay. So there it is. There's the formula for that line, right? Okay. So what did we need there to write down that formula? Not much information, right? When we're writing down a formula for a line, right? Okay. We can get away with as little as what? Just what? To write down the formula. What information did I have in this problem? Yeah, I had a point, but not just one point, right, Nadine? How many points did I have there? 2, right, okay? So if you have as little as 2 points, right, okay, you'll be able to write down the formula for a line. That kind of makes sense logically that we should be able to do that, right, okay, because if you're given 2 points, again, geometrically, you know that there's only one line that contains those 2 points, right, okay? And so if there's only one line that contains the 2 points, if I got the 2 points, I should be able to write down the formula for the line, and indeed, that's exactly what happened here, right? We were able to write down the formula for that line. Okay, now so I promised you a little shortcut there, right? Okay, to this process. Not that it's that complicated. So the shortcut is not that big of a shortcut, but I think it will help us avoid sometimes some arithmetic errors, okay, if we use the shortcut. But it's certainly not required, all right? Okay, but before we get to the shortcut, I have to go out of order here just a little bit, all right? So I've got to switch away from the topic of lines for a moment. Then we're going to come back to showing you the shortcut, all right? So I skipped this before because, again, it was, to me, out of order, but I've kind of run out of options here because we've got to do this homework that's due. All right, we've already solved this problem now long before the first test, right? This question is just write down the domain of this function, okay? So this isn't a linear function, obviously, right? It's got all kinds of wiggles in it, but we just want to write down its domain. So we know that's easy, right? Because that function starts where on the x-axis, apparently? -3, right? And extends up to, where does it appear on the x-axis there? It goes up to what? 5, right, okay? And so notice -3 is going to be included in the domain because you've got the closed dot here, but we have an open dot very carefully drawn there, right? So that means that 5 is a boundary for the domain, but it's not included in the domain. So technically, you can't use 5 as an input for this particular function, all right? So, all right, so that's easy enough to see. So now we can write down the domain. I guess the way we would have written this on the first test, right, would be as an inequality, correct? So we would say that x has to be greater than or equal to -3, okay? But at the same time, you want x to be less than 5, right? Okay, so x has to be, our domain values x, right, have to be between -3 and 5, okay? All right, so that's pretty simple. So what I wanted to show you here is not how to find the domain of this function, because we know that, but instead how to write down the domain set. So we're going to be frequently in the class dealing with sets like this one, where the set consists of all numbers starting at some place on a number line and going up to some second value on the number line, okay? And the set will include all numbers between those two boundary values, okay? So so in this case, I sort of indicated the set by using this this inequality. All right. Another way you can write down this set is using what's called interval notation. And here's the way interval notation works. All right. With interval notation, that's exactly designed. This sort of notation is exactly built to help us write down sets like this one, where, again, we're looking at all, the set is all numbers on a number line between two given boundary values, okay? So with interval notation, all you do is write down the two boundary values, okay? And you just separate it with a comma, okay? And then, all right, so the boundary values for this set are -3 and 5. And then you're going to enclose those two boundary values with grouping symbols, either parentheses or brackets, all right? And what determines whether you use the parentheses or bracket is whether or not the boundary value is part of the set. So if you want to include a boundary value in the set, you would put a square bracket beside the boundary value. So -3 is included in this set, so I'm going to put a square bracket there. And since 5 is not included in the set, but it's a boundary value for the set, I'm going to put a parenthesis around that number. So again, -3 and 5, those are both called, I usually call them boundaries, are boundary values. And the bracket there, or the parenthesis, again, just indicates whether the boundary value is included in the set or not. That's it. That's interval notation. Very simple, right? Let's look at the range, because we're also asked for the range here, all right? So that's the set of y values, right? The set of outputs for this function. Where does the range begin at here? Can you read it there? It looks like around -4, right? Okay. So it's going to be hard to read that off perfectly, right? Okay. That's one of the disadvantages to graphs. But I think we'll assume it's about -4. And where does it look like it's going up to? Close to 2, right? Okay. So if we wanted to write down the range using this interval notation, right, you would just put down those two boundary values. Make sure you put the smaller number first, though, okay? So the boundary values have to be in numerical order. So I would put the -4 and then a comma and then a 2, okay? Now, the next part here is for the range is a little bit tricky, because we have to indicate, right, with the interval notation whether or not the boundary values are included in the set or not, okay? And so we have to make a judgment call here, because we really cannot read the graph that closely. I'm going to assume that both of the boundary values are in the range, okay, because I'm really not sure. So I'm just going to assume -4 is part of the range, and also 2 is a part of the range. But if we, so I'm going to put square brackets beside the two boundary values. But if you had put parenthesis beside the two boundary values, you know, you could make an argument that's correct as well, all right? There's only a slight difference between these two sets, right? The only difference is in this case, -4 is not part of the set, and in this case, 2 is not part of the set, right? But every other number would be the same for these two sets, okay? That's interval notation, see, pretty straightforward, right? Here also is a pretty easy one. So again, we just want to write down the domain and range, right? But we want to do that using interval notation instead of using an inequality, or instead of writing it down in words. We could also write it down in words pretty easily. So where does it look like the domain starts for this set? Can we read it there? At -3, right? Okay. And notice that a curve is not cut off here over on the right-hand side. So I'm going to have to assume I'm not certain, but I'm going to have to assume that that curve is just continuing in the same pattern, right? Like this, something like that, okay? And so where does the domain end at? Infinity, right, okay? So that's pretty easy to write down in interval notation. You'll start at -3, right? All numbers beginning at -3 and going up to infinity. So there's the symbol, right, that we use for positive infinity, right? That sideways 8, okay? Keep in mind, that is not a number, though. There is no number infinity. That is just the notation that we use to indicate this idea, right, that domain is extending indefinitely to the right, okay? All right, so but now we have to put the parentheses or the brackets in. So what goes beside the -3 here? Parenthesis, right, because it's very clearly drawn, right, in the graph that left boundary value is not part of the set. So beside the -3, you're going to put parentheses, and you have to put parentheses beside the infinity, okay, because there is no number infinity. So you cannot include that in the set, all right? There's no way to include that in the set. So beside an infinity, or you can also use negative infinity sometimes when the domain is extending in this direction to the left indefinitely, but make sure always beside infinity you put a parenthesis. Don't put a bracket, okay, because that will be slightly incorrect. Even if you've got the right idea, that will be slightly incorrect. What about the range here? So let's write that down. So where does the range begin? 0, right, okay. And where does it extend to? Yeah, again, infinity, right? Except infinity going up the y-axis, right? Okay, instead of to the right on the x-axis, right? This curve is apparently continuing up indefinitely, right? So the range extends to infinity. And so remember now, you cannot include infinity in the set. Whether or not 0 is part of the range, again, that's kind of a judgment call there. I'm just going to say it is, all right? Because it's not really clear from the graph. You know, does that graph really go all the way down and touch 0, or does it just miss 0 by a little bit, right? Okay, hard to read that, right? That's one of the disadvantages of the graph. So we're not always able to be precise, okay, about our answers looking at graphs. But they give us nice estimates, right? We can write down the range there really quickly, right, without hardly any work at all. Okay, so that's kind of the idea of interval notation. So probably for the remainder of the course, you'll frequently get the instruction when you're asked to write down a set. So interval notation is about writing down sets, okay? You'll frequently get the instruction, write down the set using interval notation, okay? And so that means using this style, okay, rather than writing it out in words or trying to write it down in inequality. Let me show you another application of interval notation. Oh, by the way, when you want to write down all real numbers using interval notation, so that's a big set, of course, but that's a set that we frequently refer to, all real numbers. In interval notation, that's going to look like this, right? Okay, that means everything between minus infinity and positive infinity, okay? So that interval is all real numbers. Let me show you another application of interval notation. So not currently, okay, but eventually, after we finish with Chapter 2, we're going to get back to dealing with functions that aren't always straight lines, okay? So this kind of a question doesn't really apply to too much to straight lines, okay? But if you have curves that are not straight lines, okay, we frequently like to write down or discuss sort of the direction of the curve, okay? what I mean by direction of the curve is the curve going up, or where is the curve going up, or is the curve going down, or where is the curve going down. We usually think, when we say going up or down, we think of as we're moving from left to right through the domain, or as we're moving from left to right along the x-axis, is the curve increasing, right, or is the curve decreasing? And interval notation gives us a nice way of, often, a nice easy way of answering that question, okay? So let's look at this very simple curve. This is called a parabola, so we're getting ready to get back in Chapter 3 to talk more about parabolas, because that's sort of the simplest type of curve that's not a straight line, okay? It's almost a straight line, right? It's kind of like a straight line that's been bent in the middle. All right, and so for this parabola, we want to answer where is it increasing, where is it decreasing, or if it's neither increasing nor decreasing, that would mean if it's perfectly flat, not going up or down, where is it perfectly flat? That's constant, okay? All right, so as you're moving from left to right, let's see what's happening to that curve initially. Again, think of yourself as moving from left to right across the coordinate system, right? What's the behavior of that curve? What's the direction of that curve? Yeah, so initially here, right, Montel, on the left, as we're moving from left to right, what's happening to the curve? Is the curve going up, or is the curve going down? As we move from left to right, okay? That's right. So at first it's going up, correct? Okay, yeah, right. And then at some point it changes direction, okay? But initially it's going up. Initially it's increasing, all right? All right, so we want to describe where it's increasing, okay? But we always give our description in terms of the x-axis, not in terms of the y-axis. So you want to give your description from left to right, okay, where the curve is increasing. All right, so where does it start increasing, Montel, apparently, as we're going from left to right?
Well, it starts increasing when it starts moving forward from the, I believe that's a negative 1 to 1.5 to negative 1. Then it moves more into the positive area when it starts to...
Okay, yeah. All right, yeah, you're talking about the outputs, right? Okay, but just yeah, I don't really have to think about the sign of the outputs there, right? Okay, just what is the direction of the curve? It is, which way is it going, up or down? Up. It's going up, right? Okay, it is going up. Okay, my question is, where does it start going up? Negative infinity, right? Okay, because this, see, the reason Montel, Nadine answered like she did is we don't have this curve cut off on the left, okay? So we have to assume that it's just going to continue in this fashion on the left. Maybe we're wrong, but that's kind of what's indicated by the picture, all right? So that's what we have to assume. So that means then that as you continue, right, see, all the way out to negative infinity on the x-axis, right, as you start moving from left to right, that curve is always going to be going up, right, okay, as you're moving from left to right, okay? So it starts increasing at negative infinity, all right? Okay. That's where it starts increasing. Now, but where does it stop increasing? Where does it switch direction? X equals what? 1, right, okay? Right there at x equals 1, correct? That's where it changes direction. Because from there forward, it's doing what? Decreasing, right, okay? From that point on, it's decreasing. So, we can answer this question now, okay? Here's how you would answer this kind of formally. You would say the function or the function f, but I don't think I gave a name to this function, so let's just say the function. So the function is increasing. We don't say going up, okay? That's my informal language, all right? The function is increasing, and then you would say on, or you could also say over, and then you just write down the set. remember, that's in terms of the x-axis. So y'all told me it started increasing at minus infinity on the x-axis, right? And continued up to where? 1, right, okay? So it stops there at 1. Notice I'm writing this down as a interval. All right. Here's now where there's a slight ambiguity, okay? The question is 1, should that be a part of the set where it's increasing or not, okay? But that's clearly where the direction changes, right? All right, so look, there is some disagreement among mathematicians about what the answer to that question is, okay? The question is 1 in the set or is 1 not in the set, all right? I would say 1 is in the set, okay, right? So I would put a bracket beside the 1, okay? Sometimes, though, some textbook authors have a different view, and they will put a parenthesis beside the 1, okay? All right, so I've forgotten now what this author believes, okay? I think the author wants a parenthesis there, all right? But maybe it's a bracket. So you get on your homework, when you're asked this question, try both, okay? Because sometimes it may grade it correctly and sometimes not, all right? If you're looking at one of the homework videos that I made, I would put a bracket there, okay? But when my math lab is grading your assignment, right, your problem, they may be expecting a parenthesis. So you may have to try both ways, all right, see what it's going to grade correctly. On a test, I'm fine either way, okay? All right. As I mentioned, there's really no accepted correct answer there in mathematics for whether the 1 is included or whether the 1 should not be included. Where is it decreasing now? So as you're moving from left to right, right? Where is it? Where is the curve going down? Yeah, from 1 to infinity, right? Okay. Right. The rest of the domain, okay, it's going to be decreasing. So again, you might write a bracket there, or you might put a parenthesis, okay, at the 1. But it clearly extends to infinity, right? And there has to be a parenthesis beside the infinity. You cannot include infinity in a set in either case. This point right here at the top, right, where it switches, right? That's going to be that's usually a very useful point to know for a function, and I always like to call that a turning point, because that's where it's changing direction, right? From, in this case, from increasing to decreasing. Let's try this one. So again, I just want to write down where is the function increasing, and where is it decreasing, and possibly where is it constant. Is this function constant anywhere? Yeah, right in the middle, right? Remember, constant functions are horizontal lines, right? So this function is constant right there in the middle. It's not going up or going down, right? And so, well, let's write down that set first, okay? So so the function is constant, right? And what is that set? Where does it start? So where does it start being a flat line? 2, right, okay. So it starts there at 2, and that extends up to where? 5, right, okay. And so again, we may or may not include those boundary values, right, in our interval. So even if you wrote parenthesis 2, parenthesis 5, that would also be a correct answer. Let's see, what's it doing on the left? Decreasing, right? Okay. So because the curve is going down, right? So the function is decreasing. And what's that set where it's decreasing? Right, that's negative infinity to 2, right? Because that's where it started being constant. So decreasing on minus infinity to 2. And then there's only one other possibility, right? The rest of the function must be increasing. So it starts increasing right there at 5, right? And then apparently continues to infinity, because again, see, the curve is not cut off there on the curve is not cut off there on the right hand side. So the best we can do in trying to answer this question is just assume that that straight line is going to continue, right? Okay, so that function will continue to increase all the way to infinity. Remember now, this is real important. You've got to always write your answers to this sort of question. Be sure you give it in terms of the x-axis, not in terms of the y-axis. So it's real easy to say the function is decreasing. The function is decreasing from infinity to down to 1. Okay. Because you're thinking, oh yeah, the function is way up here at infinity and it's going to go down to 1, right? Okay? But that's not the way you answer the question. Or it might be easy to say, oh, where is it increasing? Well, let's see, it starts at 1 and it starts increasing and it goes to infinity. So it's increasing from 1 to infinity. Okay? All right, so, in some sense, that's correct, right? Okay, the lowest y value is 1, and it goes up to infinity on the y-axis. But again, that's not the way you're going to answer the question, right? You always give the answer in terms of the x-axis, right? It's these sets are sets on the x-axis, not on the y-axis. So be careful about that, okay? Don't make that mistake. That's right. And when you're talking about where it's increasing or where it's decreasing, you give your description in terms of the x-axis. Yeah. Okay. I know that seems sometimes counterintuitive, right? Okay, but that's just the accepted practice. All right. Oh, by the way, now one little technical point here and here. Those look, again, like turning points, okay, right? Because there's definitely a bend in the graph right here at these 2 points. But these are not classified as turning points. So those are not really turning points. To have a turning point, it's got to switch from increasing to decreasing or decreasing to increasing. But if it switches from decreasing to constant, that doesn't count as a turning point, okay? So you only have a turning point where you have a change in the direction from increasing to decreasing or vice versa, okay? So these points, they don't really have a special name, okay? Right, okay? They're kind of important points on that graph, but we don't have a special name for those 2 points. All right, let's look at one more here. I think there's one more. Oh, no. Okay. Well, we'll leave that example. All right. I think one more example will be enough here. All right, so here you've got plenty of wiggles. Okay. And now here we do have a complete change in the direction, right? So this point will count as a turning point, and this point will also count as a turning point, okay? Because we have a complete change in the direction. What is the change in the direction at this turning point from which direction to which direction? Increasing to decreasing, right, okay? And from here, it's going to switch back, right, okay? At this turning point, you have a switch from decreasing to increasing, okay? So those really are legitimate turning points. So where is the function decreasing? On what interval? -2 to 2, right. Okay, so it starts decreasing at -2, right there at that turning point, and continues decreasing, right, until you get to the second turning point right here, where it switches back to increasing, right? And so this function is never constant. Most of the functions we're dealing with won't ever be constant. So let's see if we can write down where it's increasing, okay? That's a little bit tricky because there are two pieces, right? There are two places, two intervals where it's increasing. It's increasing at first, right, over here on the left. So we would write that set down how? As what? So where does it start increasing? -infinity, right, and continues to -2, correct? Because that's where it starts decreasing. And then where's the second place where it's increasing? 2, right? Okay, up to infinity. Now, so we've got two places where it's increasing. There are two sets. So what we want to do is combine those two sets. The way you combine sets in mathematics is by creating what's called the union of the two sets. That just conglomerates the two sets, okay, and gives you a bigger set. The way you indicate the union is by using a kind of little stylized U here. And you can see where that symbol comes from, right? It's kind of like the letter U for union. It's not quite the letter U, though, okay, right? It's kind of an adaptation of the letter U. And that just means we've combined these two sets, these two interval sets. So the function is increasing both here and on the second set, the second piece as well. Okay, so there's a little practice with interval notation. It's a real convenience, so we'll find it handy throughout the rest of the course for writing down sets. Not always. Sometimes sets are easier to write down in other ways, but a lot of the sets we'll be working with, domains and ranges, where a function is increasing or decreasing, those sets are easy to write down with interval notation. All right, okay, so that was just a little bit of a detour there, because mostly right now we're talking about straight lines, and it's usually not very informative to talk about where a straight line is increasing or decreasing, right? Okay, because straight lines are always either increasing, right, or they're always decreasing, or they may be always constant, right? You can have a flat line, all right? So lines do not switch from increasing to decreasing or vice versa, right? Lines do not have turning points in them, right? That's why they're straight, okay? They don't have bends or turning points in them. So a line will be increasing possibly from -infinity to infinity if its slope is positive, or it will be decreasing from -infinity to infinity if its slope is negative, or it will be constant from -infinity to infinity. What makes it constant? What's the slope if the line is constant? So what's the slope of a perfectly flat line? What? 0, right, okay. So if the slope is 0, then the line will be constant from -infinity to infinity. Okay, all right, so here's the shortcut I promised you, all right. how to write down a formula for a line in just a couple of quick steps, all right, rather than going through that full process that we looked at in the previous two examples. All right, so what I'm going to do for you is we're going to derive a formula that we can use to write down the formula for a line, okay? So this is a little bit funny to describe. I'm going to create a formula that I can use to write down the formula for a line. So it's a formula for a formula. And here's how I'm going to create this formula. I'm going to go through the process of writing down the formula for a line given 2 points, but I'm not going to tell you what the coordinates for the 2 points are. I'm going to leave those as variables, okay? And so we're going to go through that process of creating the formula for a line from 2 points, but I'm not going to fill in specific values, specific coordinates for the 2 points. So we're going to do a little bit of algebra here, because algebra is when you do arithmetic with variables, correct? So we're going to do some algebra here, and this is really one of the things that makes algebra so powerful. All right, it's going to by using a little bit of algebra, we're going to save ourselves a lot of work in the future. Okay, all right, so let's see if we can go through these steps, right? So I'm just thinking I've got 2 points, right? I've got 2 points. Here are the 2 points that I'm given, right? Okay, and I'm going to write down the formula for the line, right? So we're just going to go repeat those steps, right, that we used in the prior 2 examples. So let's see, from the 2 points, what was the first thing that we had to calculate? Well, no, let me back up a little bit. What's the first thing that we recognize that we're going to write down, right? We're going to write down the formula for a line, and what does the formula for a line look like? Yeah, it looks like y equals mx plus b, right? Okay, so I wrote that down first, right? I've got to remind myself, right, that I'm going to end up with a formula like this, right? Y equals mx plus b, correct? And now all I have to do is fill in what? The m, right? Okay, and the b, right? And the b. Well, all right, so we always start by filling in the slope first, right? And how do we calculate the slope? There it is, right, okay? So there's my calculation for the slope, right? We take the difference in the y-coordinates of the 2 points that were given. Here are the 2 points that were given, right? So I take the difference in the y-coordinates, and I divide that by the difference in the x-coordinates, right? Okay, so there's the difference in the x-coordinates. That's how I compute the slope. All right, so there we've done the second step, right? First step was, oh yeah, we have to have a formula that looks like this, because this is a formula for a line, so I got to fill in the m and the b. Now I'm going to fill in the m, right? Well, there's my calculation of the m, all right? The only thing I cannot do here is actually carry out the arithmetic, right? I can't carry out the arithmetic here in the slope formula, because I'm not using specific values for x1 and x2 and y1 and y2. But nevertheless, if you did have specific values for those coordinates, that's the computation you would do. All right, now what's the next step? So after you've calculated the slope, then what do you do with that? Plug it in, that's right, okay? See, now you know the slope, right? So now you're going to put it into this formula, right? So now we're going to plug the slope into that formula. All right, well, let's do that, okay? So I'm going to plug the slope in to that formula. So I get y is equal to my slope. Here's my slope, right? y2 minus y1 over x2 minus x1, right? Times x, right? Okay, plus the b, all right? So now we've got our partial formula, right, written down. That's exactly the same steps that we did in the prior example. All right, now what's the next thing we have to determine? The what? The y-intercept. That's right, right? See, I've already filled in the slope, correct? I've already filled in the slope. There's the slope. So next I have to figure out what that b value is supposed to be, right? Okay? I got to figure out what that b value is. All right, now how did I determine before, in our prior examples, how did I figure out what the b value was? I plugged in a coordinate, right? Okay, Arthur, that's what I'm going to do next is plug in a coordinate. All right, so pick one of your points, right? You pick one of your 2 points, and you're going to plug in the coordinate. Well, which of those 2 points do you want to plug in the coordinates for? See, there are my 2 points, right? Okay, there are my 2 points, right? So which of those 2 points do you want to plug in the coordinates for? X1, Y1? Great, okay? We could have used X2, Y2 just as well, right? Okay? Because both of those points are on the line. So you plug those coordinates into your partial formula, right? So I'm going to take this point, and I'm going to plug the coordinates in here. All right, so let's see. What goes in here now? So what goes in for Y? What now? Y1, that's right, okay? That's the Y coordinate. And what goes in, oops, this is minus. What goes in now for X? X1, that's right, okay? So you're plugging in those 2 coordinates, right? And don't forget now, here you have left over there is B, okay? All right, so what you've got left over there now is B. Oh, wow, okay? So what do I now have to do with this equation? I plugged in all the information, though, okay, right? Didn't I plug in all the information there, right? So, well, what now?
You like distribute and like combine like the like ones?
Well, okay, so I think you're describing a process for me, right? Okay?
Yeah.
So, right, okay.
I forgot.
But what's that whole process? What's the point of that whole process? Once we've got those things plugged in, right? Okay. What do we have to do at this point? Do what now? So what's the next step here? Remember, remember in the prior example, once we had plugged in the slope, okay? Once we had plugged in the slope, right? Then what did we do? We solved for what? B, that's right. Yeah, okay. We solved for B, correct? Okay? So we want to take this equation now and solve it for what?
Y-intercept.
Yeah. So how do we solve that equation now for B? Well, I do want to isolate the B, right? Okay? I do want to isolate the B. So how can you isolate the B here, Arthur? Subtract what? Well, I have a better way, okay? We already have B there, just plus B on the right-hand side, correct? So how can I get just the B by itself there on the right-hand side? That's right. So subtract this, correct, from both sides, right? Okay? So just subtract all of that from both sides. All right, so what does that leave us there? You have what? Y1 minus all of this, right? Yeah, just all of this. So there's the value for There's the value for B. Okay, let's see. So that's it, right? Okay. We know how to calculate M, right? Right? Yeah, because we have a formula for M, and that is the value for that the y-intercept is always going to turn out to be. Okay. Now let me make this look a little bit cleaner for you. Okay. Again, what is this? What is this computation here for? That's really the slope, right? Okay. So rather than writing down this big fraction, because that looks a little bit intimidating, correct? Okay. Let's just fill in our common name for the slope. What is our common name that we use for the slope? M, right, okay? So rather than writing this big fraction there, let me just replace this by M. That'll make it look a little bit simpler. So I have what? B is equal to what? Y1 minus M times X1. Does that look a little bit easier now? Okay. There's how you always calculate. There's how you always calculate the y-intercept, right? Okay. It's always going to be the y-coordinate of one of your given points, right? Minus the slope times the x-coordinate of that point. Oh, okay. All right. So now let's put that into our formula for B. Okay. See, now I know what B is. So I'm substituting now the second time. So I have what? Y is equal to, again, what is all this called? What's all this called? The slope, right? That's the slope times x plus the B value. But what's the B value here? It's this, right? So it's y1 minus m times x1. Okay? Keeping in mind, right, m is the slope. All right, I'm going to rewrite this now a little bit. Let's put these two terms side by side. So I'm going to write mx minus m times x1, and then I'm going to put the y1 on the far right-hand side. So I just rearranged these two terms, okay? Put this term here and put the y1 here, right? The reason I did that is, look, both of these terms contain what factor? What factor? M. So that M you can factor out of those two terms. There it is. Yay! That's what I was looking for. That's another way, a fast way, I claim, of writing down the formula for a line, okay? Still, you have to know 2 points, okay? But when you know 2 points, here's a fast way for writing down the formula for a line. So what do? You just have to calculate what? The slope, right, okay? And then, where do the x1, y1 come from here in this formula? One of the points, that's right. You just plug in the coordinates from one of your points, right? Okay. So see, notice here you don't have to go through that step of finding the b-intercept, right? Finding the y-intercept, right? By solving an equation, because that's already sort of condensed into this formula. So see, this is really quick. You do still have to calculate the slope, but now using one of the points that you know, you just plug those into this formula, and there you've got it. There's the formula for the line, okay? Or a formula for the line. This is called, by the way, this is called the point-slope formula. That's a formula for writing down a formula for a line, okay? So let me summarize this really quickly for you, all right? We now have 2 formulas for writing down a formula for a line. The first one we learned is the slope-intercept formula, okay? Right? So if you know the slope and you know the y-intercept, you can write down the formula for a line just filling in the slope and the y-intercept, right? So that's the familiar y equals mx plus b format. That's the first one we learned, okay? But this second formula also gives you an equation for a line, all right? Okay? This is called the point-slope formula because what you need to know is a point on the line, but it can be any point. It doesn't have to be the y-intercept. And the slope of the line. You still got to know the slope of the line. And you just fill that information into this equation, and you also have a formula for the line, right? Okay, so that's the slope, and the x1, y1 is the point that you're given, okay? So you have to know a point and the slope, right? So the x1, y1 is some given point on the line, okay? So the only kind of difference between these two formulas is they both require the slope, okay? But this formula requires a point on the line, but it's a very specific point on the line. It's the y-intercept, okay? Right? This second formula is a little bit more general. It requires the slope, but you can use any point on the line. It doesn't have to be the y-intercept, okay? And many times you won't know the y-intercept, all right? You'll just know some point on the line, but not the y-intercept. So you can use this formula still to write down the equation for the line, okay? Just in one easy step almost, okay? Maybe a couple of steps. Let's use this really quickly. I think we already did this problem, but let's do it again. All right, so let's write the formula for this line that passes through these 2 points, okay? -5, -8, and 6, 3. But we want to use our point-slope formula because neither of these points is the y-intercept, right? All right, so first we have to calculate what? The slope, okay? So you must calculate the slope. So take the difference in your y-coordinates. So you can go 3 minus a -8, or you can do -8 minus 3. It doesn't matter. And then take the difference in the x-coordinates. Make sure you do it in the same order, though. All right. So here I'd have to subtract 6 minus a -5, since I did 3 minus a -8 in the numerator. Let's see. This becomes 3 plus 8 over 6 plus 5. So we get a very nice slope there, right, of 1. So easy. Okay. So easy slope there, 1. And that's it. To write down the formula for the line, you're just going to have y equals the slope times, in parentheses, x minus, and then you have to put in the x-coordinate of one of your 2 points. So pick one of the 2 points, it doesn't matter which one, and fill in the x-coordinate for that point. Let's take this one since both of these are positive, okay? So I have x minus 6, and then just plus the y-intercept of the same point, which is 3. That's it, okay? There is an equation for this line. It is not in slope-intercept form, so I cannot read off the y-intercept of this line from this equation, okay? I can read the slope, though. I know the slope is 1, right, okay? But I don't know what the y-intercept is. But that still counts as the equation for the line. If you graph this equation, you will get the line that passes through these 2 points, okay? All right. So, see, you don't have to go through the process of discovering always the y-intercept to write down the formula for a line. Actually, any point will do to write down the formula for the line. But you are going to have to know the slope, okay? So the slope is necessary. All right. We have run out of time. Okay. So for lecture. So let's stop there and take 2 or 3 minutes because we're going to finish activity 4 today, okay?